Okay, hi everybody. Can everyone hear me okay? This is my first time streaming on Twitch, so I hope it goes okay. I am obviously a novice at this, and I will probably make several mistakes, so sorry about that ahead of time. Uh, I'll ask you also, is my screen legible? So can you read the code okay? And that's not the code we're going to start with, but just as a sample. Okay, great. Excellent. Okay. So what we're going to talk about today is make it bigger. Okay, here's one make it bigger. So let me make it a little bigger then. Preferences. Let's do 20. Better? Okay, thanks JSB. Appreciate the notification about that. So what we're going to talk about today is constraint satisfaction problems, and this comes from chapter 3 of both classic computer science problems in Swift and also classic computer science problems in Python. Both of these books are books for people who either are a little bit rusty on their computer science but have been programming for several years, or maybe people who never had a computer science education and they're working as programmers or doing programming as a hobby and they want to get kind of a general survey of several different computer science topics. So one topic we cover in the book is constraint satisfaction problems. Today we'll go through some code about them in Python, and then at the end I'll do a Q&A about the books or about anything about computer science education you want to talk about. I'll introduce myself a little bit. So my name is David Kopek. I am the author of Classic Computer Science Problems in Swift and Classic Computer Science Problems in Python, as well as Dart for Absolute Beginners. I work as an assistant professor of computer science at Champlain College. I teach a wide variety of computer science courses, and I'm really excited to be with you and to get a chance to talk to you a little bit about constraint satisfaction problems and the books in general. So what I thought I'd do is I would have both a combination of the code that we'll kind of go through from the book, and I also would actually show you some diagrams from the book directly that are relevant to what we'll be talking about. So I'll kind of be switching back and forth a little bit between some of the diagrams and some code as well. And I'll be watching the chat in case anyone has any questions as we go. So what is a constraint satisfaction problem? Well, a constraint satisfaction problem is what it sounds like, something where you have a problem that has some constraints. But what is a constraint? So before we even talk about that title of the chapter, constraint satisfaction problems, let's talk about the general idea of variables and domains. So a variable is just like a variable in programming. It can be something that holds multiple different values, but at any one time might be holding just one value. And we want to ideally set variables to the right values to solve some kind of problems. But what kind of values can we actually set the variables to? Well, that's the purpose of domains. So domains tell us these are the possible values for these variables. So I have an example up here. This is a type of problem that constraint satisfaction problems are used a lot for solving, a scheduling problem. So we have some variables. In this case, our variables are actually different people, and maybe the people who need to make some meeting. So Mary, Joe, and Sue are our variables. And the domain might be the times that those variables are available for the meeting. So perhaps they're available between 2 and 4 p.m. or something like that. And then the constraints, that's where this actually becomes a constraint satisfaction problem. Those are the requirements between the variables that need to be true in order for the problem to be solved. So in this problem, we have constraints about who needs to be at the meeting. Sue and Mary need to be at the meeting, or Joe can be at the meeting. So we could have Mary and Joe, or we could just have Joe, or we need to have Sue and Mary. We need to have Sue and Mary, and we could have Joe with them, or we could not have Joe. But one constraint is we must have Sue and Mary, and the other constraint is we may or may not have Joe. So if we can find a way to find meeting times, in other words, domains for all three of these people, and we can satisfy that the right people via those constraints can be at the meeting, then we can solve the problem. So this happens all the time. I mean, you think about when you use like Google Calendar or you use Apple iCal, and they don't call it iCal anymore, right? Now it's Apple Calendar. They're trying to figure out different people's schedules and a time that they next are all available. They're solving a constraint satisfaction problem like this. So this one is a little more involved. We're going to solve some simpler ones over the next few minutes. But before we do that, let me show you the beginning of our Python code for going through a constraint satisfaction problem. And then we'll go into some specific constraint satisfaction problems. So our Python code starts with defining what a constraint is. So and you'll notice I use type hints throughout this. And I'll just say something about type hints. Type hints, in my mind, add clarity to, especially when you're reading code. They make it longer when you write code in Python, but I think they add some clarity when you're reading code. But I will say it was the most controversial decision I made around the book, was putting type hints in everywhere. And some people love type hints. Some people really just find them a little cluttering and they make the code a little bit more verbose. But I use type hints throughout here. If you're not familiar with type hints, you can actually just read the code without the type hints, and it's basically just standard Python for you without the type hints. So anytime you see a colon, that's adding in a type hint. But if you just take out the colon, it's just Python without the type hints. So, not a lot going there. If you've never seen type hints, it should be okay. And sorry, my dog was barking a little bit. Anyway, so a constraint. A constraint is something between variables, right? They're the things that are constrained are the variables. So this constraint class is really simple. All it has to do is take a list of variables and then make sure that all of them are satisfied. But for a generic constraint, a constraint that isn't specific to a certain kind of problem, we don't know what it means for that constraint to be satisfied. So if this was a scheduling problem, that satisfaction might have to do with that all the variables, certain of the variables are available at that time. But for other kinds of problems, there's going to be different factors that go into whether or not the constraint is satisfied. So we're going to end up overriding this method satisfied in subclasses of constraint that are implemented for our different kinds of problems. Okay, so that's our constraint. Then we have the general structure for holding the entire constraint satisfaction problem together, and we call that the class CSP. And CSP is a generic class again, because we want to be able to work with different types for both the variables and the domains. So our variables might be strings, or they might be integers. Our domains might be strings, they might be integers, they might be something else altogether. So depending on the type of problem, we're going to have different kinds of variables and constraints, and domains. And this is going to differ depending on the specifics of the problem. And so this is where you start to see some Python type hints coming into play here. So this is in Python type hints saying that V and D could be any specific type. We don't know what type they are at the time that we're defining the class, but in the future, the user of this class is going to specify some types for V and some types for D. And that type has to be the same throughout the subclass. So variables will always be of some type for some particular type of problem, and domains will always be of some type for some particular type of problem. So what does a CSP do, though? It gathers together variables, domains, and constraints. It's responsible for associating variables with domains and responsible for ensuring that all of the constraints are actually satisfied. So that's what this constructor is doing. It's just assembling variables, domains, and constraints as dictionaries so that we can look them up later on. And then when we want to add a constraint, we actually have a method here, add constraint. And what it will do just is do a sanity check and just make sure, hey, this constraint is between certain variables. Do those variables actually exist in the problem? If the variables actually exist in the problem, then we're good and we can add this constraint in. If it's not, that means there was something wrong in the construction of the constraints. That's really just a sanity check there. Nothing more sophisticated going on. Okay, so far we've just been doing setup. Now we get into the real stuff. So consistent. What's consistent? Consistent looks to check if every constraint for some particular variable. So remember, different constraints are going to be associated with different variables. So constraints for some variable, let's say it was our scheduling problem. Let's say all the constraints around Joe. So the different constraints that limited Joe's applicability to a meeting. Are all of those satisfied? If they are, then that's good, and that means that we have a good solution so far for the constraints for this variable. If they're not satisfied, we're actually going to have to go back and try some different domain values for this variable to try to solve it. And the way that we're going to do that is through what's called a backtracking search, which is actually our next method. So I'll go into that in a minute. But I do want to mention, look how nice it is to be storing everything in dictionaries, because we can easily just look things up by the variable, right? So we can just quickly look up, these are the constraints associated with this variable. Okay, so then this is the most sophisticated, although it's not that sophisticated, this is the most sophisticated part of the constraint satisfaction problem, the backtracking search. This is the real meat of it. This is the part that actually does something. So the backtracking search is responsible for trying to find domain values that can go in for each of the variables that will satisfy all of the constraints. So how does it work? Well, every time we do a backtracking search, we have some kind of assignment. So those are potential domain values for the variables. And if we have the same number of assignments as we have variables, that means we've actually assigned everything. That means that every variable has some assignments. So we found a domain value that fits in for every variable. And that's a great thing. So in that case, we're done. And we actually return the assignment because we've successfully assigned every variable to a domain value. However, most of the time until we finish, that won't be true. And so we just keep track of here which variables don't yet have an assignment. So which variables have we not yet found domain values for to go into them? That's what unassigned is here. And we use a little list comprehension in Python here to do that. Then how do we actually go and do the search to see what domain values might be applicable for this variable? Well, this is actually, if you've seen depth-first search before, a depth-first search algorithm before, this is a form of depth-first search. What we do is we first look at the first unassigned variable. We keep track of that in a variable here, a Python variable now, not a constraint satisfaction variable. Then we go through all the potential domains for that variable. So we're just going to go through them one by one in the original order that they were put into the domains. And for each of them, we create a new potential assignment, taking the old assignment, because the old assignment will have the domains for all the previous variables, and we add in this just one new variable's assignment. And we add that to this new, what we call local assignment. And if it turns out that, remember that method we did, consistent, which checks all the constraints? If it turns out that this new assignment combined with all of the old ones together is consistent, so that means all the constraints are satisfied, then we're good. And that means this was a good assignment. And in that case, we call backtracking search recursively. And what will happen is then, let's go back to the top here, the assignment will now become what was the local assignment, now with one more variable successfully filled in with a domain value for it. And that means that now we can move on to yet one more unassigned variable, or if we're totally done, we'll just return the assignment. So it's actually a pretty simple recursive depth-first search going on here. If you're not familiar with depth-first search, I could understand that this would look pretty intimidating. But great news is depth-first search is actually covered in Chapter 2 of the book. So we cover depth-first search in Chapter 2 of the book, and then in Chapter 3, in constraint satisfaction problems, we kind of assume that you have that knowledge about depth-first search. But basically, depth-first search, let me give you an idea about it as an analogy in the real world. So if you had an onion and there was something like inside of your onion somewhere, maybe there was some insect crawling around inside of it. It's kind of a nasty example, but I'll do it anyway. There's some insect crawling inside of your onion and you want to find it, right? There's two main strategies you might use. There's breadth-first search, where you might kind of peel the onion back one layer at a time, looking for that insect. And then there's depth first search, where you might just kind of stick a knife into the onion and you hope you found it. You just went really deep, really fast, and you weren't doing it super methodically. You went and you tried a bunch of values, tried a bunch of places to search for it, and you didn't quite find it. So then you backtrack to the last place you were and you stick the knife in a little bit differently and hope you found the insect that way. It's not always the most efficient way to do things, and this is not the most efficient way to necessarily to solve a constraint satisfaction problem, but it is it certainly works, and it's one that's very simple to illustrate, which is why we use this method in the book in chapter 3. Okay, so now let's use this framework to try to solve some specific actual problems. So this was all just build up to be able to try to solve a problem, but let's try some actual variables, some actual domains, and some actual constraints. So I'm going to open back up the preview here of some of the problems from the book, and let's look at the Australian map coloring problem. So here's the problem. We have the nation of Australia, and Australia has multiple different regions. I think some of them are territories and some of them are provinces, but I'll just call all of them regions. And what we want to do is we want to color each of the different parts of Australia with a different color. And we're going to have 3 different colors that we can use. We can use maybe blue, green, and red. So the question is, can we make the computer automatically color them for us so us as human beings don't need to do it? Not that this is like a very hard problem to do as a human being. In fact, if you try doing it yourself with a blank map of Australia, you can probably do it in just a few minutes. But it's often used as a first problem in constraint satisfaction problem solving education, I guess, or teaching, because it's so easy to think about and reason about. So if we think about this, what are our variables and what are our domains here? So the variables would be each of the different regions. And we could think about them as just strings in our program. So they could be strings like Western Australia. The string Western Australia could be one of them. That's a variable. Northern Territory could be a string. What are the domains? The domains are what colors we could fill in for those variables. So we have 3 different colors here. We have red, green, and blue. So the domain is actually going to be the same for every variable, because Western Australia could be red, green, or blue, depending on how we solve the problem. South Australia could be red, green, or blue, depending on how we solve the problem. Now, what's the constraint? Well, that's where the problem actually gets interesting. The point of this is that we don't want to have, and I should have maybe said it at the beginning, we don't want to have any of the 2 regions next to each other having the same color. So we want to make sure that every 2 regions next to each other have a different color. So we want Western Australia to have a different color from Northern Territory, but we also want Western Australia to have a different color from South Australia. So we want to make sure there's always no 2 regions that border each other, are adjacent to each other, that have the same color. So that's going to be our constraint. So now that we have a constraint satisfaction problem solving framework, how can we actually now codify the problem and the constraints? So actually, I think before we even look at the constraint, let's look at how we codified the variables. So my variables here are just a list of strings, each string representing one region of Australia. The domains are just going to be strings that represent the different colors. So the domains can be red, green, blue, and they can be red, green, or blue for any of the regions. And so we're just going to go through all the variables and assign the domains red, green, and blue to all of them. It was that easy. Now that we have this framework in place, it was that simple to define variables and constraints, and we've actually just defined almost the whole problem. The last part is the constraints. So the constraints are that we don't want to have 2 regions next to each other that have the same color, right? So before I go and we look at all this code for adding all the constraints, let's look at how a constraint is actually defined. So a map coloring constraint is a subclass of the constraint class that we looked at earlier. And remember that constraint we said before was generic in that the variables and the domains could be any type. But now in this problem, we have specific types. We know that all the variables are going to be Python strings. They're going to be things like Western Australia, Northern Territory. And we know that the domains are also going to be strings. They're going to be things like red, green, or blue. And so when we end up subclassing constraint here, we can actually now fill in the types. And string is going to fill in for the variable type, and string is also going to fill in for the domain type. So therefore, a map coloring constraint is going to be a constraint between variables that are strings that have domains that are strings and other variables that are strings that have domains that are strings. So when we initialize a new map coloring constraint, what we want to provide it are the two places. So remember, it's always going to be between two adjacent regions of Australia. So that's going to be places like Northern Australia and Western Australia. That's going to be places like, Northern Territory. Sorry if there's any Australians listening. Things like Northern Territory and South Australia. It's always two of them that we're constraining. So that's what place 1 and place 2 are. And then how are they satisfied? Well, we want to make sure that they don't have the same domain. So they don't have the same color. How do we check that they don't have the same color? Well, it's this really simple line here, not equal to. How simple is that, right? We want to make sure that red is not equal to green, right? We want to make sure red is not equal to blue. Blue is not equal to green. We want to just make sure that they're not the same string. You might wonder, why is this first line in here? Well, we can't even do a check if we haven't yet assigned both of them. So, for example, if I've assigned a color for Western Australia, but I haven't yet assigned a color for Northern Territory, then there's really no way for me to actually check between the two of them whether the constraint is satisfied. So in that case, I just return true because I want to keep going until I actually have some kind of assignment for both of them. But once I have an assignment for both of them, it's as simple as just checking that it's not the same assignment. So it's really straightforward. Then here's the code for actually adding in all the constraints. Now this part was done manually, right? So there was no way to automatically know. It would have been cool maybe if I'd used some machine learning and read in a map file and it automatically figured out that this region has this name and it's next to this region that has this name. But here we just manually, this is basically our map. This is us manually adding constraints in for each of the adjacent regions. So we're adding in Western Australia to Northern Territory, et cetera, right? Victoria to New South Wales, because they're next to each other, Victoria to Tasmania. So any two that are adjacent, we need to have a constraint between them. So we just added in all these constraints here. Then we're just calling methods on what we defined earlier. Remember earlier on we defined the Constraint-Satisfaction class to have the backtracking search method. We're just searching through, and if we found a solution, we print out the solution, and if we didn't find a solution, we print out no solution found. So let me try running it, and let's see what the results look like. So it colored them successfully. So first of all, we know that because it didn't just print out no solution found. And the solution is that Western Australia should be red, Northern Territory should be green, South Australia should be blue, et cetera, et cetera, et cetera. And that is, if you look here, that's actually what we illustrated here in the diagram in the book was the solution, obviously. So, okay, you might be saying that seemed like a lot of work to solve that problem. That seemed like you did a lot of setup there, a lot of preparation to solve what looks like not that hard a problem. Well, what I think is more interesting here is how we can reuse that same framework now to solve different kinds of problems. So let's solve 2 or 3 other problems that look quite different from the map coloring problem using the same exact framework. And what I'll do for that is I will go over to the next diagram so we can illustrate the next problem. So this is called the 8 queens problem. Here's the challenge. You have a chessboard, and what you want to do is you want to actually place 8 queens on the chessboard so that none of them are threatening each other or attacking each other, depending on what your parlance is. So this is an actual potential solution here. Now, for those of you that don't play chess, the way that queens work is they can actually move both diagonally and they can also move vertically and horizontally across columns and rows. So they're the most powerful piece in the game, and they can just glide across the board to any square that's within a diagonal that's not blocked by something within a row or a column. So in this case, if you follow the diagonals, let's say we follow the queen on c7. If you follow the diagonals, or you follow the row here or the column, you'll see there's no other queen within any of those places. So therefore, this is a queen that that is a good part of a solution to the 8 queens problem because it's not threatening or attacking any other queens. So the question is, can we place all 8 of them on the board without any of them threatening or attacking any other queens? And there's actually more than one solution to this problem. So there's actually many different boards that have the queens in different places that successfully solves a problem. But we just want to try to find one solution. Can we just find one solution to this problem? So we won't go back to CSP because we already solved that. That's the great thing, right? We already know what a constraint satisfaction problem looks like. What we can do is we can now just define different kinds of constraints, and then we can solve totally different kinds of problems. So using the same framework. So here we have a queens constraint. And a queens constraint is going to be between variables that are integers and the domains that are integers. Why is that? Well, we can actually think about the variables in this case being the different potential columns that the queen could be on. So that can be like columns A through H on this board, or we just use integers. So, and in computing, we usually start counting at 0, right? So we could also think about it as columns 0 through 7. And the same thing for the rows, right? We can think about these as being rows 0 through 7, or I might have actually done 1 through 8 in the code. I need to remind myself. I did 1 through 8. So 1 through 8 can be the columns, and 1 through 8 can be the rows. So the CSP then is going to then end up associating each of the queens on different columns. And by the way, we know all the queens have to be on different columns, right? Because if any of the queens were on the same columns, they would be attacking each other. So we know right off the bat, it's like a little trick that we have to put every queen on a separate column, right? But then what we don't know is which row to put them all in once we've already put all of them into separate columns. Hey Teal, hi from USA. Nice to see you from Spain. So knowing that all these different queens are on different columns, how do we figure out the right row? Well, again, we can just have our CSP do a backtracking search to solve that. So we've set up all the columns as our variables. We've set up the different possible rows as our domains. And then we just implement a CSP that has a constraint satisfaction problem that has columns for the variables, rows for the domains. Really straightforward. But then we have to add in the constraint. And this time you'll notice it's a different kind of constraint. So in the map coloring problem that we looked at before, the constraint was always between 2 different locations on the map, 2 different regions of Australia. Now, this problem, the constraint is actually between all of the different variables at once, right? The constraint is actually that we have to look at every queen at the same time because we're not just looking at 2 at a time. It's good if 2 of them are not attacking each other, but we want each of them to not be attacking all the other queens. So it's a different kind of constraint here. It's a constraint where we're looking at actually a list, perhaps, of all the different potential queens. So how do we satisfy that constraint? How do we satisfy a constraint between all of the possible different queens? I don't think there's some other problems I want to cover, so I don't think we have to go through this in a huge amount of detail, but I'll go through it in a little bit. We look at the column and the row of each queen. And so you could think about this as the first queen. So this is like queen 1 column, queen 1 row is what I meant by the Q1C, the Q1R here. Then we look at each of the other queens. And so I call the other queens like Q2C is queen 2 column and queen 2 row. So we're going to end up looking at Q1C and Q1R for one queen, and then Q2C and Q2R is going to be each of the other queens. So we have a total of 8 queens, right? So the first queen is going to be always Q1C and Q1R, and then the other 7 queens are going to one at a time be Q2C and Q2R. Hey Max, good to see you. So having Q1C and Q1R together with Q2C and Q2R, we can then just compare them. And again, this is like in the Australian map coloring problem. It's a simple check. We just need to check they're not the same, right? If they are the same, that's not good. That means we have not solved the problem. If we have 2 queens on the same row, obviously we haven't solved the problem. The other check here is for diagonals. And using absolute values here is just a quick way of checking if the 2 are on the same diagonal. So in other words, here we're checking, are these 2 queens on the same row? If they're on the same row, that's not good. We didn't solve the problem. And then in the second one, we're just checking, are these 2 queens on the same diagonal? If they're on the same diagonal, we also did not solve the problem. However, if they're not on the same row and they're not on the same diagonal, and then we've gotten through comparing this queen to all the other queens, then we've successfully solved the problem, and that means that we return true. So again, it's a simple comparison, and the machinery for doing all the searching was already implemented by backtracking search back in the constraint satisfaction problem. So here we can do a totally different kind of problem and solve it using the same framework. So let me try running this, and we will see what we get. Now, this might look a little cryptic, but what this is here is this is each queen at some potential column with the row that it should be on to solve the problem. So we solved here that the queen on column 1 should be on row 1, the queen on column 2 should be on row 5, the queen on column 3 should be on row 8, and if we followed all of these and put them on the chessboard, they would not be attacking one another, and we would get a position that looks like our final diagram here, which is having all the queens on places where they're not attacking any other queens. So I hope you see that, at least in my mind, this is quite a different kind of problem than the Australian map coloring problem, but because we're able to break it down into variables, domains, and constraints, we can solve it using the same generic framework. Okay, let's try another problem. So we've done the Australian map coloring problem, we've done the 8 queens problem, which are both pretty classic problems. Here's a problem that everyone, I'm sure, is familiar with. This is a word search. So in this problem, we have different words that we want to put in a grid of letters. And we want to make it so that the words are legally within the grid of letters without necessarily overwriting one another, for lack of a better word, right? So they need to safely all be able to fit in there successfully. So how can we fit different size words all into this grid is basically the challenge of the word search problem. Now, this one's a little bit more involved, and so I think I'm going to go through the general outline of it and how it uses the constraint satisfaction problem framework, but I won't go through maybe the details of how we constructed every part of it. So let me open that up. Sorry, going to the wrong chapter there. Word search. Is this similar to linear programming? Yes, linear programming can be thought of as a more advanced technique than this generalized backtracking search to solve constraint satisfaction problems. But yeah, in linear programming, you also have constraints between variables. Usually they're logic constraints between variables. And so there's a very significant overlap between constraint satisfaction problems and linear programming. It's a great question. So to figure out a word search, in this case, we have a few different helper classes. We have a grid location, that's like a location on the word search grid somewhere, a row and a column. We also have a grid, and a grid is just going to be a two-dimensional, what in other programming languages we call a two-dimensional array, but in Python we call it a list of lists. So a list of lists of strings, where each string is really just going to be a letter. So I could have maybe used a character or something like that, but it's really just a single letter somewhere on the grid. So having a grid of letters, having locations on the grid, then we start to have these methods for constructing a grid. And again, I won't go into all of these in a huge amount of detail, but what this is basically doing is generating a random grid by using some built-in nice stuff from the Python standard library. And this is just displaying a grid, it's just printing it all out. Then we get to the parts that are actually related to a constraint satisfaction problem. So generate domain. Generate domain is going to go and figure out for one potential variable. And I should have said, what is a variable in this? Well, let me have you think about that for a second as I go back to the problem here. What is actually one of our variables? What do you think? A variable would be one of the words that we want to put on the grid. So in this case, we're putting names on. So like Sarah would be a variable. Matthew would be a variable. The domains are all of the potential places that we could put that variable on the grid. So for example, it depends if we start counting from the bottom or from the top here, but let's say we started counting from the top going down and from the top from the left going to the right. So we could say that Matthew was actually placed at location like 1, if we start counting at 0, right? And then each of his individual letters was placed at some additional locations as well. That's really the domain, is like where are the potential places that we could put a word in the grid. So again, this is like a different kind of problem, right, than the 8 queens problem or the Australian map coloring problem. But you'll see we're able to solve it using the same framework. Okay. So I won't go into all the details here because I do want to get to one more problem after this. But generate domain looks through the entire grid and tries to find locations that it could potentially put one of those words. And it gathers together all those different locations that words can go. And those cumulative locations are the potential domains for each of the variables. So those are the places that we could put those words. Those are the places we could put the words. That's the domain. And then what is a constraint in this case? A constraint is going to be a check to make sure that we're not putting words on top of each other, right? I don't want to put the word for the first letter for Matthew is an M, right? And the first letter for Sarah is an S, right? If I overwrite the M with an S, then I actually do not successfully construct a word search problem, right? So I need to make sure that I'm not overwriting one letter with another letter from a different word. And so actually that's pretty simple here. All I'm doing here is again just checking that we don't have any of them on the same location. And how do I do that? Well, this is a convenient trick that you use in programming a lot, is if you want to eliminate duplicates, you can just change over from a list to a set. Or if I was in another programming language, I'd be saying I'm going from an array to a set. Anytime you go from a list to a set, or in another programming language, an array to a set, you're going to eliminate duplicates because by definition, sets are not allowed to have duplicates of the same value. So what we end up with in the end is we end up with just the non-duplicated locations for some assignments, and we check, is that the same number of locations as we originally had in the assignment? If that's true, that after eliminating duplicates, we still had the same number, that would mean that we didn't actually have any overlaps. So I hope you see here how the converting things to a set is really helping us check for duplicates. And then by checking for duplicates, we're actually checking that nothing is overlapping or overwriting one another. So I hope that you can kind of see how that fits together. But look how compact that is, right? Just 2 lines of code, and we've checked that we don't have any overlapping locations. Look how simple word search constraint is, right? This is where we're overriding, again, something from the original CSP problem that we looked at the beginning of the stream, right? And the types, again, it's a generic type, and I know not everyone loves the type hints, but let me just mention how the type hints fit in here. We're saying that the variables in this problem are strings. And remember, those are, again, the words. So in our example, I'll open up the example again. That's like Matthew or Mary or Sarah. Those are all strings, right? And then the places that Matthew can go or the places that Mary or Sarah can go, those are grid locations. And we looked at the grid location class earlier. And so the cumulative places that they can go is a list of grid locations. And so a list of grid locations is what makes up the domain for each of those variables. Okay, so we defined our word search constraints. We defined what the actual variables are. And in this case, I just used those variables, Matthew, Joe, Mary, Sarah, Sally. There's just strings. We define what the domains are. We use that method generate domain to figure out all the potential different places that each of the words can go. And then we generated a CSP just as we did before. And again, the CSP class doesn't change. It's the same exact class for solving all these different kinds of problems. And we added in a word search constraint to make sure that none of the individual words ends up overlapping or overwriting one another. And then we just run a backtracking search. And it's that simple. If we were successful, then we're good and we can go printing out the final grid. If we were not successful, then it turns out that probably we had too many words, or we had some words that were so long that they couldn't fit within the grid with other words. And so they ended up having to overwrite each other, and so we couldn't find a way to put them all in. But let's try running it here. And of course, I chose an example where I knew we could solve it. But here you see a solution at the bottom here where we've managed to fit all the different words that we wanted to fit in here somehow. I see Matthew's up here. Here's Sarah. I think Joe is upside down here. And there's probably some more in the other, well, they must be. The other ones must be in there as well. Anyway, okay, so that's another totally different kind of problem, but because we could still define it using variables, domains, and constraints, we could still solve it the same way using a backtracking search and a constraint satisfaction problem framework. Let's do one more, and this will be our last one, okay? And then I'll take some of your questions about the books or about computer science education or anything else you'd like to talk about. But our last kind of problem is another classic problem. It's called sen plus more equals money. And maybe you tried to do this some point in a math class when you were growing up, maybe in elementary school or middle school, probably middle school. You tried to solve this problem at some point. It's a cryptarithmetic problem. And what that means is we have characters that are supposed to represent digits. And so let me make this even bigger because it's probably a little small for you on the screen. So we have sen plus more, and each of these letters is supposed to represent a different digit 0 through 9. So for example, maybe D is supposed to be 4, hypothetically, or maybe E is supposed to be 7. Then anytime that we see that same letter, we expect the same digit to be able to fill in to make the problem and its solution true. So anytime we see an E, we expect there to be a 7. So if there was going to be a 7 here, we expect there to also be a 7 here, and also a 7 here. If we can find digits that can fit in for each of the letters, then we can successfully solve the problem. So before I go and show you the code, I want you to be thinking about this right now. What is the variables here? What is the domains? And what are the potential constraints or the constraint between all of these? There might just, I'll give you a hint, there might just be one constraint in this case. Although I could think of a way you could formulate it with multiple constraints, but there's one really obvious constraint here. But what do you think the variables are? What do you think the domains are? And what do you think the constraint is? And let me go, because we're not going to run out of time. I am going to open it up. We're already at 7:42, and I did want to leave some time to take questions about the books. So let's go right into it. So I'll take away the suspense. The variables could potentially be all the different letters. Okay, so each of the individual letters could be our variables. The domains would be the digits that can try to fit in for each of those letters. So each of the letters could potentially be the letters 0 through 9. We don't know what the right answer is yet, but that's what they potentially could be to solve the problem. So notice the constraints, by the way, we don't, in the variables, we don't duplicate our letters, right? Because even though the E ends up being in the problem 3 times, right? There's only one letter E that we're trying to solve for. Even though we see the letter E 3 times, there's just only one value that we're trying to find for letter E because it's going to be the same value in every location, right? Okay, so let me just go back now to the code. So we have our domain, we have our variables. Last part, as you've seen the pattern now, right, is we always have to have a constraint. So the constraint in this case, the send more money constraint, is really, really straightforward. In fact, it might be our most straightforward constraint other than the Australian map coloring problem that we did earlier. It's really straightforward because the problem spells out the constraint for you. The constraint is that whatever values we assigned for the letters, this equation has to be true. Send plus more has to equal money, right? That is the constraint. So what do? Let's just do a little bit of arithmetic. For whatever letters we've assigned, whatever digits we've assigned to the letters, let's just do the arithmetic and see if they solve the problem. And that would be a solution to our constraint. So let's see here. Looking at satisfied, the first thing we'll check is have we actually tried assigning some value to every letter? So until we've actually tried giving every letter a value, there's no point in actually doing the arithmetic, right? Because if I don't have a value, there's nothing for me to add up. So I need to actually have values. But once I have all the different potential values, let's see what I can do. Well, I can actually construct the equation here. How can I construct the equation? Well, look at where each of these items is, right? If this was just a number here, right? This would be the D would be in the ones place. The N would be in the tens place. The E would be in the hundreds place. And the S would be in the thousands place, right? And so what I can do is I can just multiply each of the potential digits by its placement numerically, and I will end up getting the number that together they represent. So I end up calculating what send represents, I end up calculating what more represents, and I end up calculating what money represents using the domain values that have filled in for the variables that are represented by the letters. Then I just check, is send plus more equal to money? If they are, this means that we actually have solved the send plus more equals money problem. How easy was that, right? It was so similar to some of these other constraint satisfaction problems that we've done, and yet it's so different. It's so different in that when you look at this problem, right? When I look at this problem, I don't see a map. I don't see the Australian map coloring problem. So you have to realize what are variables, what are domains, and how can they be constrained between each other. But there's a huge wide variety of problems that can actually be solved this way. Anyway, let's try running this and try seeing if we have a solution. Of course, I know we do. And if it doesn't run right now and doesn't give us a solution, that's really bad because it's in the book, right? So anyway, so here's a potential solution. So if you go and fill this in, you'll see that this actually ends up being send plus more equals money. And I'll show you that. I think I have, of course, I would have put this in the book. It's after the end here, the solution here. You know what I should have done? This is a good thing for the second edition of the book. I should have lined up the numbers again here, right? I should have lined up each of the numbers again and spelled out to prove to you that they actually solve for one another. But anyway, if you line up the digits and you put them in the right places now, you'll see it does add up. Send plus more does equal money. Anyway, so we made it through 4 different constraint satisfaction problems. And the key thing I want you to take away is that we were able to use the same backtracking search and the same very simple framework for setting up a constraint satisfaction problem to solve all of them. I imagine in your software development tasks, whether you're a professional software developer or a hobbyist software developer, you come across problems that could be solved using this framework. I'm not saying that the version that we implemented here is the most efficient way to solve these problems. It's not necessarily. And there's other extensions to constraint satisfaction problems that we could talk about, but probably beyond the scope of today. Things like rearranging the order that we look at the constraints in to go through them as efficiently as possible, or going through the variables that have the most constraints put on them first, or the least constraints put on them first. That kind of ordering can actually make us go through the potential solutions more quickly. And then there's also a whole different way, not using a backtracking search, but using a totally different method that's way beyond our scope today called forward checking that can sometimes be more efficient in trying to solve one of these problems. If you want, now my book is a book that gives you a really broad overview of different kinds of problems. It's not a deep book in the sense that I'm not going to explain to you every single different way to solve a constraint satisfaction problem or every way to make it more efficient. I'm going to just introduce you to the idea of a constraint satisfaction problem, show you a real way of solving them as we did here. And then if you want to go further, of course, there's whole books on the subject. One I would recommend is Artificial Intelligence, A Modern Approach, covers constraint satisfaction problems in chapter 6 of that book. So if you want to go in a lot of depth into this, chapter 6 of that book is great. But if you just want to get the first introduction, chapter 3 of my book is a great first introduction. And you can also, Manning is offering that for free right now through live books on the website. And we also have an article that is linked to from the from the Classic Computer Science Problems in Python page that goes through this as well and kind of walks you through the code. And all the code I went on here today is on my GitHub repository for the book. So if my GitHub username is DaveCom, I should have put a link in somewhere. I can do that in the chat later. But you can go on my repository, DaveCom, DAVECOM, find Classic Computer Science Problems in Python repository, and you'll find all this code on there as well. Okay, now that we made it through this, I'd like to take questions about the books, about computer science education, about anything else you want to talk about. So I'll look at the chat and see if anyone's asking any questions. And if we don't, I have some pre-made questions that I'll answer if nobody has any questions. Oh, and thank you. So I just saw in the chat that there's a link to my repo that Manning's already put up. So you can go check that out, and there, you can get all the code from today's presentation as well. Okay, since I'm not seeing any questions, I'll go through a pre-made question. Okay, so let's say the question was, who are these books suitable for? And that's one of the most common questions that I get, is who are these books suitable for? So the Class Computer Science Problem Series is not for beginner programmers. So it's not really for people as their first book in programming. It's for people who already have an intermediate or advanced knowledge of the language in question. So Class Computer Science Problems in Swift, I wouldn't give to somebody who's just going into Swift for the first time. I would give it to somebody who's already been probably doing Swift for like maybe 6 months to a year, then pick up Class Computer Science Problems in Swift, because it's really more about using the language as a vehicle to learn the computer science topics and the problem-solving techniques more than it is about learning the language. So of course there's tons of great books about learning Swift. There's several good books from Manning. There's also Apple's free book, which is an all right book as well. But once you've picked up those first books, then go on to Class Computer Science Problems in Swift when you want to learn more about computer science, but using Swift as a vehicle. Same thing for the Python book. You don't have to have a computer science education though. So you don't have to be somebody who had a 4-year degree in computer science to read these books. In fact, a large part of the number of people that read the books are people who didn't go to school for computer science, and they want to know what these topics are about. They want to know how to solve different kinds of problems appropriately. They want to know when their colleagues or friends talk about different programming, problem-solving techniques, what they really mean. So actually, self-taught programmers is one of the biggest audiences of the books. But with that in mind, you do need to already be a programmer. You can't come into the books never having programmed before. Okay, so I see a couple questions here from the chat. Let me answer a couple of them. The first one, with the depth-first search, what's the size of the problem that start causing some performance problems, and what would be the best way to solve it? Well, that's a great question. Let me give this to you in a real-world example that'll help you see why depth-first search can sometimes not make that much sense. Let's say I was trying to find the least number of train stops between Boston and Seattle in the United States. For those of you that aren't from the United States, Boston is on the far eastern seaboard of the United States, and Seattle is on the far western side of the United States. Now, New York is also on the eastern seaboard, and it's pretty close to Boston. Okay, and actually, let's change the problem a little bit. Let's say I'm trying to find a train that goes from Boston to New York. That's much closer together. Okay, depth first search. We don't specify that we're first going to check the closest locations to Boston. We're just going to go deep right away. So maybe we first go from Boston to Montreal in Canada, and then we go to Toronto in Canada, and then we end up at Seattle, and then we go from Seattle all the way back to New York on the East Coast. Using depth first search, that could potentially be a solution that we find, which would not be great. That would not be the best way to get from Boston to New York by train. Using breadth first search, we would first look one station away from Boston in every direction. So we'd first maybe go from Boston to Bangor, Maine, and we first go from Boston to Concord, New Hampshire, or Montpelier, Vermont, or something. And then we'd go from Boston to New Haven, Connecticut. We look at these places just one stop away from Boston. Then we'd look at places 2 stops away from Boston. Maybe when we got to 2 or 3 stops away from Boston, we'd get to New York. With depth first search, we might have dug really far in the wrong direction before we got to the place we were looking to go. With breadth first search, we would have carefully and methodically gone one space out at a time till we got to the location that we really wanted to get to. And so that's just one example of a situation where depth first search, might not be the most efficient way to solve a problem. But for problems where you don't have that many variables and that many constraints, it's fine. The problems that we've dealt with today, as you saw, when I ran them, even on my laptop here, they were answered instantaneously, right? So if you have a problem with only a few variables, only a few domains, only a few constraints, up to let's say even a dozen or more, there's this. Even though this technique is not one that I would use in production on some big data set, if you have a simple problem like the ones we went through today, it's perfectly legitimate to use a simple depth first search as we did with the backtracking search. Okay, let me go to the next question here. And there's all kinds, I want to say also, there's a really good explanation of depth first search versus breadth first search versus the A-star algorithm, which is a much more advanced algorithm, in chapter 2 of the book. Actually, I think it's one of, it's my book, so of course I'm going to say it's good, right? But I think it's one of the best parts of the book is chapter 2 of the book goes through depth first search, breadth first search, and A-star search. And I think it's a pretty strong part of the book. Okay, next question here. Is there any reason you picked Swift as a programming language for the book? Okay. So when I originally did the first book, I was working on it in the 2016 to 2017 timeframe. I finished at the end of 2017 and it came out at the beginning of 2018. And at that time, I was thinking about this series as bringing computer science education to emerging languages, so languages that might not yet have good computer science books in them. Now, that was true at that time in Swift, and so I thought, okay, I'm going to be a niche. I'm going to be the first computer science book for Swift. And that book did okay, and I think it's a great book. But it turns out that there was actually a much bigger demand for this type of book than I thought. People were looking for something that was somewhere between a tutorial and a textbook. They wanted something that was more approachable, that was broad, that dipped into a lot of different computer science topics correctly, importantly, of course, verified by technical reviewers and a great real publisher like Manning. But they didn't want something that's as boring and hard to get through as a textbook. And so the publisher said to me after we did the Swift book, which was, the Swift book was pretty successful, they said, we got to bring this to a much bigger audience. And so then we did the Python book. And the Python book has just been really successful. It's been a bestseller for Manning. It's been translated now into 7 different human languages. That came out at the beginning of 2019. And so we see that there's really a demand in the large languages, like the really popular languages, to have a book like this. And so we're actually porting the book next to Java. I'm working on that right now because we're doing just the next really big language, right? And we did a poll of our readers. We said, do you want the book in, we've done the book in Swift. We're doing it in Python. This was back in the beginning of 2019. Do you want the book next in Java, C#, JavaScript, Rust? There were people who wanted it in Haskell, all over the place. And I actually thought maybe we'll do it in Go, and a lot of people wanted it in Go. But we realized based on the poll and also based on market research that the best next language to bring it to was Java in terms of the number of people that were looking for something like this probably. So we're doing class computer science problems in Java, and that's going to come out at the end of this year. Okay, next question here. What would you recommend as further learning research areas after getting through one of your classic computer science problems books? Well, thanks for that question. That's a really good question. I would say the next thing you would want to go to after that would be a deep book on data structures and algorithms if you haven't already done that. So I'm going to recommend a few different books. If you want a more informal style, kind of like my book, then I'm going to recommend Grokking Algorithms, which is a Manning title. And Grokking Algorithms is a really good book. I've read it myself. I think it's excellent. And I actually use Grokking Algorithms when I teach data structures and algorithms at the college level. I don't use it completely. It's not a deep enough book to cover every subject in it, but I use it for part of the course. And I think Grokking Algorithms is an excellent Manning title, and really props to the author. I think it's Aditya. I forgot the name off the top of my head, but he did a really fantastic job. So Grokking Algorithms is probably the next book I would go to after mine. And it's also in Python. So if you're doing the Python book, it's really great. But if you're not doing the Python book, it's also easy enough to read Python code that you could totally understand it, even if you're not a Pythonista. If you want to go deeper than that, then there are, of course, the classic data structures and algorithms and artificial intelligence textbooks. And the class computer science problems books, they touch on both data structures and algorithms, and they also touch on artificial intelligence. We get into topics like neural networks in them and clustering and things like that. But so if you want to go even deeper into those, I do think the classic textbooks in those areas are pretty good. So the most classic textbook is probably Introduction to Algorithms by CLRS. Shout out to Tom Corman if he's reading or watching. He was my professor back in college, and he wrote one of those textbooks, or most of one of those, or a significant portion of one of those textbooks. And it's a great reference, Introduction to Algorithms. If you like math, it's really pretty deep on the math, but it does everything in pseudocode. If you're looking for something that's a little more, a little less mathy and a little bit more easy to read and in real code, I recommend Algorithms by Sedgwick, which is actually in Java and is also used a lot in college classrooms, just like Introduction to Algorithms is. It's just a little bit more readable for some people, but it depends what your disposition is more. Would you rather see the code in a real programming language, or would you rather see the code as pseudocode with math? Those two textbooks are the two standards, really. Introduction to Algorithms by Corman, and I don't know what the LRS stands for, I forgot off the top of my head, and Algorithms by Sedgwick and Wayne. Those are really the two best, probably, algorithms textbooks. But I think Grokking Algorithms is a good place to start. If you want artificial intelligence, I recommend the classic book, Artificial Intelligence, A Modern Approach, which is the standard artificial textbook. If you want a more approachable textbook, my dad, who's actually deceased, unfortunately, but he wrote an artificial intelligence textbook a few years ago that's called Artificial Intelligence in the 21st Century. And that's also a pretty good artificial intelligence textbook, which is more approachable than the classic text. Artificial Intelligence, A Modern Approach. So but all those textbooks are good. Sorry, I went on a huge tangent about textbooks. Let me go to the next question. Next question. When I was going through the book, I was learning a lot of new syntax that wasn't the normal guides. How do I learn more in-depth parts of a language? For example, the underscore being in front of the functions to make them hidden. Okay. All right. Great question. So there's a book I'm recommending a lot of books today, but the book that I'm going to recommend for getting deeper into Python syntax is Fluent Python. Fluent Python. Now, maybe Manning doesn't like this, but it's actually an O'Reilly book, unfortunately. But Grokking Algorithms, really great Manning book. Fluent Python is an O'Reilly book that I do recommend, and it's really excellent, and it goes deep into every little facet of Python syntax. I don't think it's the type of book you have to read the whole thing from cover to cover. I didn't do that. You can just go into the chapters that interest you or that are important to the type of syntax that you're interested in, but Fluent Python will really teach you to write in a Pythonic way. Okay, let's see. Are you expanding into other languages? I already answered that. We're expanding into Java next. That's going to be our next language. And I know there's people that want other languages, so we'll see how the Java book goes, and we might continue to go from there. What do I think of Algorithm Design by Kleinberg and Tardos? I haven't read that one. I hear a lot about that one, but I've read a lot of other algorithm books, or at least skimmed a lot of other algorithm books. I've read cover to cover a few of them, but I haven't read that one, so I can't comment on it. I've heard good things from other people, though. Okay, what language would you say are better to begin to experiment writing a domain-specific language with? Oh, that's an interesting question. I wouldn't say that that's really my area of expertise, so I don't want to guide you wrongly. I've seen people build domain-specific languages in a variety of languages. I know that some people love to build them in functional languages like Haskell. I personally, that's not my cup of tea really, but there are some really good libraries in Haskell for doing that. But I think it's the language that you're most comfortable in when you're first starting out in any topic. That's what I find. Now, I have written programming books now in 3 different languages and working on the 4th. My first book was in Dart, then I did Swift, then I did Python. My professional career was largely in iOS development, so doing a lot of Objective-C and then Swift, and then doing Python a lot for web projects. But I think anytime I start a new topic, so it's good to start in a language that I'm really comfortable in. And so sometimes being more comfortable in a language, I think outweighs having a really good library sometimes. Like having an okay library in a language that you're an expert in sometimes is nicer than having a great library in a language that you're really going to struggle with. Just to tell a little war story, I did a startup when I was just out of graduate school. So this was like 8 years ago. And I went and the project was being built in Ruby on Rails. And I came and joined and I had to take over the project. And I was not an expert in Ruby and I was not an expert in Ruby on Rails. And I had to learn it on the job as I was going. And Ruby on Rails is a great framework. But I probably would have done, having a lot of Python experience already at that point, I probably would have done a lot better in a lesser framework in Python than working in Ruby on Rails because I was a newbie to both Rails and to Ruby. So I would just say in general, my general advice to students usually is when you're starting a new topic, better to pick a language that you're an expert in at first, than to pick a language just for its library, unless the library is so good. You have to weigh it, of course. There's pros and cons, but maybe I went on too much of a tangent there too. Okay, I think that's all the questions we have, and we've gone just over our hour. So I'll just give a final couple of plugs. So I'll just say that, first of all, I hope that you'll check out the free chapter for Manning. Chapter 3 is out there on the live book, and there's also the article, Constraint Satisfaction Problems in Python, which is a free article based on Chapter 3 that goes into this in more depth. I will also give a shout out to my Twitter, at Dave Kopec, DAVEKOPEC. I try not to post anything political. I know people hate that on Twitter, so I try to stay apolitical on Twitter. And I mostly just post about computer science topics or programming, or I like business. I post about a lot of business stuff. If you ever want to ask me questions, feel free to write a tweet to me at Dave Kopec. The GitHub, my GitHub username is DaveCom. So DAVECOM. There's a link in the below from Manning. It's put up both to my Twitter and my GitHub. And that's where you'll find the repository for all the source code from the Classic Computer Science Problems books. And look out later this year for Classic Computer Science Problems in Java. I just want to really thank you for taking the time. I know everyone has busy lives, and so I really appreciate you taking the time to spend with me in the last hour talking about constraint satisfaction problems and the books. And I hope you have a really wonderful night. And I hope everyone's safe, obviously, during the pandemic, which is a difficult time to be broadcasting during, and I didn't know if I should mention it or not during the broadcast, but, I really hope everyone's okay. Okay. Have a great day.